Hello everyone, my name is Mohammed Arif AIIMS and today we'll be discussing two of the chapters in chemistry, polymers and chemistry in everyday life. So let's get into the chapter. So first we'll be discussing the chapter polymers. The term polymer is defined as very large molecules having high molecular mass. These are also referred to as macromolecules, which are formed by joining of repeated structural units on a large scale. So very large molecules having large molecular masses formed by joining of single units called monomers. See, the monomers are joined to form polymers. The repeating structural units are derived from some simple and reactive molecules known as monomers and linked to each other by covalent. So, how are polymers formed? The monomers which are linked by covalent bonds. Many monomers which are linked together by covalent bonds form polymers. The process of formation of polymers from respective monomers is called polymerization. So, the process of forming polymers from joining many monomers together to form the polymer. That process is known as polymerization. Okay, moving on. Now we will classify polymers. Classification of polymers based on the source from which polymer is derived is. So how we prepare the polymer? Based on that, we can classify polymers. One, natural polymers. These polymers are found in plants and cellulose. So these are polymers that are already found all around us in plants and animals. Examples for such polymers are proteins, cellulose, starch, some resins, and rubber. Now, semi-synthetic polymers. What are semi-synthetic polymers? These are polymers that we prepare from natural sources, but we combine them with using our chemical processes. So such examples of such polymers are cellulose derivatives, cellulose acetate, cellulose nitrate are examples of this category. So for in this chapter and in chemistry in everyday life, I think the most important factor is we have to remember the names of examples of everything. So it's sort of a mug-up. So you have no other way other than mugging in this. Synthetic polymers. A variety of synthetic polymers are plastic, synthetic fibers, nylon 66, synthetic rubbers, UNAS are examples of man-made polymers. Now, types of polymerization reaction. So here we have to learn about how we prepare polymers. What are the reactions involved? So we prepare polymers mainly by two reactions, that are addition reactions and condensation reactions. So on the basis of which reaction we are using to create the polymer, we call the polymer addition polymer or condensation polymer. So there are two broad types of polymerization reaction, that is addition or chain growth polymerization and condensation or step growth polymerization. So two types of polymerization is present here. So another name for addition polymerization is chain growth polymerization, and the name for condensation polymerization is step growth polymerization. So what is addition polymerization? In this type of polymerization, the molecules of the same monomer or different monomers add together on a large scale. So different monomers, whether it be same or different monomers, they keep on adding to the chain and they form a polymer. Such type of polymerization is known as addition polymerization. The monomers used are unsaturated compounds. Example, alkenes, alkynes, and derivatives. So in addition polymerization, the monomers will be always unsaturated compounds. This mode of polymerization leads to an increase in chain length, and chain growth can take place through the formation of either free radical or ionic species. So in this method, when we increase the chain length, so the chain length can be increased by either forming free radical or ionic species, but mainly by free radical mechanism only. However, the free radical driven addition or chain growth polymerization is the most common mode. So we will now see the mechanism, free radical mechanism. A variety of alkenes or dienes and derivatives are polymerized in the presence of a free radical generating initiator. So we always use an initiator to initiate the reaction, like benzyl peroxide, acetyl peroxide, tertiary butyl peroxide, etc. So here we will show example of synthesizing polythene later. For polymerization of polythene, ethene to polythene, we use benzyl peroxide initiator. The process starts with the addition of phenyl free radical formed by peroxide to the ethene double bond, thus generating a new and larger free radical. This step is called chain initiating step. So it is written here. We have the benzyl peroxide molecule here. So the benzyl peroxide molecule first forms free radical. We can see the bond splitting here. And we get two phenyl radical from one benzyl peroxide molecule. And this phenyl radical will go and react with an alkene, ethene in our case, for synthesizing polythene. And we get this free radical here. So up to this step is known as initiation. Chain initiating step. As this radical reacts with another molecule of ethene, another bigger size radical is formed. The repetition of the sequence with new and bigger radicals carries the reaction forward, and the step is named as chain propagation step. So what is propagation? Chain propagation step means we already got a radical here. This radical will go and react with another ethene molecule and form an even bigger free radical. It again will go and combine with n number of ethene molecules to form very large free radicals. So this step will go on until the next step, what is called as termination. What's termination? We will first see. Ultimately, at some stage, the product radical thus formed reacts with another radical to form the polymerized product. This step is called the chain terminating step. So here we have two big free radicals formed with the phenyl radical at their end. So we see for both these free radicals, the other end has a free radical there. So these two free radicals combine to form our polythene molecule. So this is how polymers form through the addition method. The addition polymers formed by the polymerization of a single monomeric species are known as homopolymers. So if all the monomers are the same, we call that polymer as homopolymer. Or if they are formed by combining different kind of monomers, so it will be called copolymers. So we already learned one homopolymer here. Polythene is formed by combining n number of ethene molecules. So for copolymer, we have an example here, which is DNAS. What it is made by combining 1,3-butadiene and styrene. So simply split the double bond, create free radicals, and combine. So we get the final product as butadiene styrene copolymer, which is DNAS, which is an artificial rubber. Now we will discuss some important addition polymers. The first one, polythene. We already saw how polythene is formed. Polythenes are linear or slightly branched long chain molecules. It can be linear or slightly branched molecules. These are capable of repeatedly softening on heating and hardening on cooling, and are thus thermoplastic polymers. So when we heat polythene, it gets soft, and on cooling, it again gets hardened. So such polymers are called thermoplastic polymers. So polythene is a thermoplastic polymer. There are two types of polythene as given below, which are low density polythene and high density polythene. So first we'll discuss what is low density polythene. It is obtained by the polymerization of ethene under high pressure. So for creating low density polythene, The pressure is almost 1000-2000 atmosphere. Temperature is 350 Kelvin to 5 centigrade. The presence of a peroxide initiator. The low density polyethylene is obtained through the free radical addition hydrogen atom abstraction. It has a highly branched structure. These polymers have straight chain structure with some branches. Low density polyethylene is chemically inert and tough but flexible and a poor conductor of electricity. It has a highly branched structure, so structure is given here. It is chemically inert, tough but flexible and poor conductor of electricity. Hence, it is used in insulation of electricity carrying wires and manufacture of squeeze bottles, toys, and flexible pipes. So, in this chapter, whatever we learn what is a monomer of the polymer and where it is used. Examples are very important for this chapter. So, low density polyethylene examples are squeeze bottles, toys, flexible pipes. For high density polyethylene. For high density polyethylene, how it is formed? It is formed when addition of polymerization of ethene takes place in a hydrocarbon solvent in the presence of catalysts such as, this is a very important catalyst, triethyl aluminum and titanium tetrachloride. Together we call it as Ziegler-Natta catalyst. Temperature is slightly lower and pressure is also low. There we used high pressure and high temperature. Here it is lower than that one. High density polyethylene thus produced consists of linear molecules. So we have to notice that high density polyethylene does not have branching. So they are closely packed. The structure is given here. Earlier we saw that low density polyethylene has some branches present, so they cannot be closely packed. So due to close packing, they have high density. Such polymers are also called linear polymers. High density polymers are also chemically inert and more tough and hard. It is used for manufacturing buckets, dustbin, bottles, pipes. So they are less flexible than low density polythene. So they will be used to make more harder plastics like buckets, dustbin, bottles, pipes, etc. Now we will discuss polytetrafluoroethene or Teflon. So we have heard about Teflon because it is used in our non-stick pans and all. Let's see what Teflon is made of. Teflon is manufactured by heating tetrafluoroethene. Tetrafluoroethene means CF2 double bond CF2 with a free radical or parasulfide catalyst at high pressures. It is chemically inert and resistant to attack by corrosive reagents. So the uses are important. It is used in making oil seals, gaskets, and also for non-stick surface utensils. That is what is mainly known for non-stick pans. They are coated with Teflon. So the reaction is given here. Now we will discuss polyacrylonitrile. What is polyacrylonitrile? So our monomer is acrylonitrile. What is acrylonitrile? CH double bond CHCl. The addition polymerization of acrylonitrile in presence of peroxide carrying leads to the formation of polyacrylonitrile. So this is what we get. Polyacrylonitrile. It is substitute for wool for making it is known as Orlon or acrylan. It is used as a substitute for wool. Now we will see what is condensation polymerization or step growth polymerization. This type of polymerization generally involves a repetitive condensation reaction between two bifunctional or trifunctional monomeric units. So here the monomers are either bifunctional or trifunctional groups. And what happens? A group gets condensed and leaves while polymerization. These polycondensation reactions may result in loss of some simple molecules. Such what molecules can leave due to polymerization can be either water, alcohol, HCl, etc. And lead to the formation of high molecular mass condensation polymers. So here we have example of dacron or terylene, how it's formed from ethylene glycol and terephthalic acid. So we can see ethylene glycol has OH group on both the sides and terephthalic acid has COOH group on both the sides. So they are bifunctional groups. So what happens here? So here we know the alcohol's OH group and the acids which combine, and what happens? Water is eliminated from here. So many such units are joined together to form what terline or background. So this is what happens in condensation polymerization. And we lose some simple molecules for polymerization of the monomer. In these reactions, the product of each step is again a bifunctional species. So even when we combine, again we are getting a new bifunctional species. See, we still have one OH group here and COH group in the opposite side. So even after polymerization, combining two monomers, we are getting bifunctional species. And the sequence of condensation goes on. Since each step produces a distinct functionalized species and is independent of each other, this process is also called step growth polymerization. So even after combining two monomers, we are getting a distinct new monomer for combining again and again. So it happens in many steps. We are calling it step growth polymerization. The formation of terylene or dacron by the interaction of ethylene glycol and terephthalic acid is an example of this type of polymerization. So this is an example of condensation polymerization. We will see, we will learn some important compounds formed by condensation polymerization. So first, we will learn about some polyamines. These polymers processing amide linkage are important examples of synthetic fibers and are termed as nylons. The polyamines are otherwise known as nylons. So how do we recognize the polymer? They will have amide linkage with them. So here we have an example of nylon 66 and nylon 6. So how is nylon 6? It is prepared by the condensation polymerization of hexamethylene diamine with adipic acid under high pressure and at high temperature. So we have hexamethylene diamine here. It combines with adipic acid here. And what happens here? Water is eliminated and amide link is formed. So this unit N times, that's our polymer nylon 66. So the use is, it is used in making sheets, bristles for brushes, and in textile industry. The next polyamide is nylon 6. It is obtained by heating caprolactam with water at high temperature. Nylon 6 is used for the manufacture of tire cords, fabrics, and clothes. When we heat caprolactam, high temperature, we get nylon 6. Now, our next example is polyesters. So we already discussed on polyester when we learned the example condensation polymer, which is terylene dacron. So these are the polycondensation products of dicarboxylic acids and diols. So what we use there, we used ethylene glycol and terephthalic acid. So it's just a dicarboxylic acid and a diol. Dacron or terylene is the best known example of polyesters. It is manufactured by heating a mixture of ethylene glycol and terephthalic acid. We already saw the example. And the catalyst is important there. So the catalyst we use there is zinc acetate, antimony trioxide, catalyst. So what is the use of terylene background? Is grease resistant and is used in blending with cotton and wool fibers. It's grease resistant and is used for making glass reinforcing materials in safety nets. Now, phenol formaldehyde polymer. These are obtained by condensation reaction of phenol with formaldehyde. So when we combine phenol with formaldehyde, we get ortho and para-directed products for with both. See, this is an ortho directed. Or this has both ortho and para, or we get tri-substituted product. So here we have to learn about two compounds which are Novolac and Bakelite. How is Novolac formed. See, any type of this monomer, the ortho isomer. We are polymerizing that to form what? Novolac. This product is not called Novolac, which is used in paints. Now, our next Novolac and heating with formaldehyde undergoes cross-linking. So when we heat Novolac with formaldehyde, it undergoes cross-linking. You will get a structure like this. It's called bakelite. It's a thermosetting polymer, which means it does not get soft on heating. So it cannot be reused or remolded. So it is used for what? Used for making combs, phonograph records, electrical switches, and handles of various utensils. We told Novolac is used in paints. Bakelite is a thermosetting polymer, so it is used in combs, switches, handles of various utensils. Or we can simply say bakelite is the what condensation polymer of this isomer. This product it polymerizes and tends to form bakelite. Next one, melamine formaldehyde polymer. Melamine formaldehyde polymer is formed by condensation polymerization of melamine and formaldehyde. So this is melamine, this formaldehyde. So we'll get the intermediate as this. Now what happens? The OH group and the NH2 group of the next monomer combines to form what our melamine polymer. So where is it used? It is used for the manufacture of unbreakable crockery. Now copolymerization. We already discussed that copolymerization means what? We use different monomers and combine them to form polymers. Copolymerization reaction which a mixture of more than one monomeric species allowed to polymerize and form a copolymer. The copolymer can be made by not only by chain growth polymerization but by step growth polymerization also. So we can make copolymers by using both the methods, addition polymerization and condensation polymerization. It contains multiple units of each monomer used in the same polymeric chain. Copolymers have properties quite different from homopolymers. For example, butadiene styrene copolymer. What do we call that? Butadiene styrene copolymer. We already discussed that is Bunas. It's quite tough and is a good substitute for natural rubber. It is used for the manufacture of the Bunas uses are manufacture of auto tires, floor tiles, footwear components, and cable insulation. It's actually a synthetic rubber. Now we will study about rubbers. Rubber. First, natural rubber. Rubber is a natural polymer and possesses elastic properties. It is also termed as elastomeric polymer. In elastomeric polymer, the polymer chains are held together by weak intermolecular forces. These weak binding forces permit the polymer to be stretched. So, rubber has what? Has weak intermolecular forces. So, when we stretch it, it comes back to its original position due to what? Due to crosslinks present in it. These crosslinks help the rubber to come back to its original position. Rubber has a variety of uses. It is manufactured from rubber latex, which is a colloidal dispersion of rubber in water. So we obtain this rubber latex from rubber tree and we use that to produce rubber. Natural rubber may be considered as a linear polymer of isoprene, 2-methyl-1,3-butadiene. That is what's known as isoprene. So when we polymerize 2-methyl-1,3-butadiene, we get natural rubber. So the monomer of natural rubber is what? cis-1,4 polyisoprene. So it's a cis isomer which is becoming the monomer for natural rubber. The cis polyisoprene molecule consists of various chains held together by weak van der Waals interactions and has a coil structure. So rubber has what? A coil structure. That's why it can be stretched and still it comes back to its original position. So this is what I had to discuss about natural rubber. Just remember that natural rubber is produced from a cis isomer. Now, vulcanization of rubber. Natural rubber becomes soft at high temperatures and brittle at low temperatures. So what rubber breaks easily at low temperature and becomes soft at high temperature and shows high water absorption capacity. It is soluble in non-polar solvents and is non-resistant to attack by oxidation. So natural rubber has all these drawbacks. So to improve this, we carry out what? Vulcanization. So what is vulcanization? So we mix raw rubber with sulfur and a proper additive. The temperature range between 373 to 453 Kelvin. So what happens when we heat? When we heat, there is formation of cross linkages. So vulcanization, sulfur forms cross-link in the reactive site of the double bond. Because of this sulfur cross linkage, the rubber gets stiffened. So the manufacture of tire rubber, 5% of sulfur is used as cross-linking agent. So it might be can be a potential question. What for manufacture tire rubber? What is the amount of sulfur used? It can be asked. So answer is 5% of sulfur is used. Now we'll talk about synthetic rubbers. We already discussed the formation of Buna-S, which is a synthetic rubber. Synthetic rubber is any vulcanizable rubber-like polymer which is capable of getting stretched to twice its length. So any vulcanizable rubber which is capable of stretching to twice its length are called synthetic rubbers. However, it returns to its original shape and size as soon as the external stretching process is released. The synthetic rubbers are either homopolymers of 1,3-butadiene derivatives or copolymers of 1,3-butadiene or derivative with another unsaturated monomer. So it can be what can be a homopolymer of 1,3-butadiene repetitive units, or it can be what it can be a copolymer also. So first we will be discussing about neoprene. What's neoprene? Neoprene is formed by polymerization of chloroprene units. So this is what is known as chloroprene units. It has superior resistance to vegetable and mineral oils. It is used for manufacturing conveyor belts, gaskets, and hoses. Now Buna-N. So when we copolymerize 1,3-butadiene styrene, it forms Buna-N. But when we copolymerize 1,3-butadiene and acrylonitrile, we get Buna-N. Okay, say it wrong. 1,3-butadiene and styrene, we get Buna-S. Okay. Buna-N is obtained by the copolymerization of 1,3-butadiene and acrylonitrile. 1,3-butadiene and acrylonitrile in the presence of a peroxide catalyst. It is resistant to the action of petrol, lubricating oil, and organic solvents. Buna-N is used for what? It's used for making oil seals, tank lining, etc. Now we'll be talking about some biodegradable polymers. So why do we need biodegradable polymers? Because most of the man-made polymers are not easily degraded by the bacteria. So they persist in our environment for a very long period. So that's why we created biodegradable polymers. So first we'll be discussing about what PHB or poly beta hydroxy butyrate co-beta hydroxy pyrite. It is obtained by the copolymerization of 3-hydroxy-butanoic acid and 3-hydroxy-pentanoic acid. Where is it used? It is used in specialty packaging, orthopedic devices, and controlled release of drugs. HBV undergoes bacterial degradation in the environment. So it's called a biodegradable polymer. So we see the polymerization here. 3-hydroxybutanoic acid and 3-hydroxypentanoic acid. It polymerizes to form what? PHBV. Now, nylon to nylon 6 is another biodegradable polymer. It is an alternating polyamide polymer of glycine and aminocaproic acid. So we'll just try to draw the diagram here. We have NH2, CH2, just glycine combines with what? NH2, CH2 5 times COH2 caproic acid. When we combine this, what happens? Here H, NH2 groups H and OH, COH groups OH combines. And we get what? NH, CH2, C double bond O, NH, CH2, 5, C double bond O, 4 N times. This is what is known as what? Nylon 2, nylon 6. Now we have some important polymers table given by NCRT. So what happens is we had nothing polymers name, the monomer and its uses. So first polypropene. So monomer is propene, uses manufacture of ropes, toys, pipes, fibers, etc. Polystyrene, monomer is styrene. What it is used as an insulator, wrapping material, manufacture of toys, radio and television cabinets. And PVC, or polyvinyl chloride. Monomer is vinyl chloride. What is used for raincoats, handbags, vinyl flooring, and as we all know, water pipes. And urea formaldehyde resin. The monomers are what? Urea and formaldehyde is a copolymer. It is used for what? It's used for making unbreakable cups and laminated sheets. Now next polymer is glyptal. This is a copolymer of ethylene glycol and phthalic acid. It is used for manufacture of paints and lacquers. Bakelite. We already discussed that one. The thermosetting polymer. Monomers of phenol and formaldehyde. Used for making combs, utility switches, handles of utensil and computers. So what I suggest you to do is what? You have to make a list of all the addition polymer and condensation polymers. And right there, make a table containing first column what? The polymer's name, second column the monomer's name, and third column its uses. Okay? Create a table like that, so it's easy for you to revise it later. Now we'll get to the next chapter, what? Chemistry in everyday life. So here we'll first learn the classification of drugs. First, on the basis of pharmacological effect. This classification based on the pharmacology effect of the drugs. It is useful for doctors because it provides the whole range of drugs available for the treatment of a particular type of problem. So, what is the use of the drug? According to that, we classify drugs such as what analgesics have pain-killing effect, antibiotics kill microbes, or arrest the growth of microbes. On the basis of drug action, it is based on the action of a drug on a particular biochemical process. So, according to the action of the drug used, we can classify drugs. For example, we have given here what antihistamines. What antihistamines? They inhibit prostaglandins, which are mediators for inflammation. So, indirectly, antihistamines are anti-inflammatory drugs. On the basis of chemical structure, also we can classify drugs. Here we have example here what sulfonamides. They have what this group here. Now on the basis of molecular targets, drugs usually interact with biomolecules such as carbohydrates, lipids, proteins, and nucleic acids. These are called target molecules or drug targets. Drugs possessing some common structural features may have the same mechanism of action on target. So some receptors or targets are targeted by a group of drugs. So according to which receptor it is acting on, also we can classify drugs. We will learn about drug target interaction. So catalytic action of enzymes. So what are enzymes actually? So we know in our human body a lot of processes are happening. So these processes are essentially what many number of chemical reactions that are occurring in a coordinated way. So we know for any chemical reaction to happen faster, we need catalysts. So in our body, these catalysts are known as what? Enzymes. So what are the action of enzymes on our body? The first function of an enzyme is to hold the substrate for a chemical reaction. So it holds the substrate. So where does the substrate bind for an enzyme? The substrate binds on the active site of the enzyme, and it holds the substrate there. So that it can be attacked by the reagent. The second function of an enzyme is to provide functional groups that will attack the substrate and carry out chemical substance. Or sometimes the enzyme also provides functional groups so that the reaction occurs faster. So drug enzyme interaction. So what happens? We are giving drugs which can alter the function of the enzyme. So we will see how it happens. Drugs inhibit any of the above mentioned activities of enzymes. These can block the binding site of the enzyme and prevent the binding of substrate, or can inhibit the catalytic activity of the enzymes. So what happens? Either the drugs can go and bind with the active site, so that what happens? Our substrate cannot bind to the active site of the enzyme. So the drugs that go and blocks an enzyme's activity, such drugs are called what? Enzyme inhibitors. Drugs inhibit the attachment of substrate on active site in two different ways. So we have two different mechanisms for this inhibition, which is what? Competitive inhibition and non-competitive inhibition. So what is competitive inhibition? In competitive inhibition, both our drug, the drug we gave, and the substrate, they compete for what? Binding to the active site. You know, the drug and substrate, they have similar structures. So what? They both compete for binding to the active site of the enzyme. So if the drug goes and binds with the active site, or substrate cannot bind with the enzyme. So such type of inhibition is what is known as competitive inhibition. Now, what is non-competitive inhibition? So if the drug, we are giving one drug and goes and binds with another site on the enzyme known as what? Allosteric site. So when the drug goes and binds with the allosteric site, what happens? The active site's shape changes. So when this shape of the active site changes, what happens? The substrate cannot bind with the enzyme. So here, this type of inhibition is called what? Non-competitive inhibition. Now we'll talk about receptors and drug targets. Receptors are proteins that are crucial to body's communication process. Majority of these are embedded in cell membranes. So what's the job of a receptor? When a substrate comes, it either allows the molecules to pass into the cell, or it transmits a message inside the cell, into the cell, so that our bodily process can happen. In the body, message between two neurons and that between neurons to muscles is communicated through certain chemicals. These chemicals are known as chemical messengers. So when a chemical messenger comes and binds with the receptor, or message is transmitted inside the cell. To accommodate a messenger, shape of the receptor sign changes. This brings about the transfer of message into cell. So how does this message transfer occur? So when the chemical messenger bind with the receptor's shape changes. That's why a message is generated there. Drugs that bind to the receptor site and inhibit its natural function are called antagonists. So drugs which bind to a receptor and block its activity, such drugs are called antagonists. So what are the drugs that supports or act like the substrate? Such type of drugs are called what? Agonists. So that mimic the natural messenger. So drugs that mimic the natural messenger are known as what? Agonists. Now we will see different types classes of drugs. First, we will be discussing about antacids. Overproduction of acid in the stomach causes what? Irritation, pain, and in severe cases, what we get? We get ulcers, gastric ulcers. So until 1970, only treatment of acidity was what? We'll give antacids such as what? Sodium hydrogen carbonate or metal hydroxides, aluminum and magnesium hydroxide. But the problem with administering sodium hydrogen carbonate is what? It makes the stomach alkaline. And when it will give a positive feedback and it causes the release of more acid. So it becomes even more severe for the patient. Metal hydroxide are better alternatives because what? Metal hydroxide does not increase the pH above neutrality. However, sodium hydrogen carbonate increases. So by giving these compounds, what happens? We can only what? Subside the pain for some time, but we cannot treat the root cause, which is what? Production of more acid in the stomach. So this production of acid in the stomach is caused by histamine. What histamine stimulates the secretion of pepsin and HCl in the stomach. So a drug was discovered called cimetidine, or otherwise known as Degamet. So it blocks the histamine with the receptors and thus inhibits the production of hydrochloric acid. So after cimetidine, another drug was also discovered, which is called what? Ranitidine. So these two are antacids, and a structure of histamine molecule is also given here. Now, antihistamines. Histamine is responsible for nasal congestion associated with common cold and allergic response to pollen. Or we can simply say inflammation is mediated by histamines or allergic responses. So we give what? Synthetic drugs called antihistamines. So examples of antihistamines are what? Brompheniramine, or another name is dimetap or dimetane, or terfenadine, Sildane. So the structures are given here. Next, we'll go for neurologically active drugs. So the neurologically active drugs we have to learn are tranquilizers and analgesics. Tranquilizers and analgesics. So what are tranquilizers? Tranquilizers are a class of chemical compounds used for the treatment of stress, mild or even severe mental diseases. So when we give tranquilizers, what happens? They relieve anxiety, stress, irritability, or excitement by inducing a sense of well-being. And they form an essential component of sleeping pills. So we have various types of tranquilizers. Noradrenaline is one of the neurotransmitter that plays a role in mood changes. The level of noradrenaline is low for some reason. So when the noradrenaline is a natural neurotransmitter in our body, so it affects our mood. So when the noradrenaline level gets low, what? Our mood is lowered and the patient suffers from depression. So in such situation, what we should give? We should give antidepressant drugs. So what do these drugs do? These go and inhibit the enzymes that catalyze the degradation of noradrenaline. So what we should do? We should retain the noradrenaline produced in our body. So for depressed people, the amount of noradrenaline is already low. So if that gets metabolized, it will become even more severe. So what we do is we give this antidepressant drugs, which go and inhibit the noradrenaline metabolizing drugs. So noradrenaline is retained in our body. So example of such drugs are what? Hyaluronic acid and phenolazine. So we can the structures of both those drugs. Now, chlordiazepoxide and meprobamate are also what? Relatively mild tranquilizers. So they are useful for relieving tension. Equanil is another drug what is used for controlling depression and hypertension. So structures are given here. Now, derivatives of barbiturate acid, we call them as what? Barbiturates. The examples of barbiturates are here. So veronal, amytal, nembutal, luminal, and seconal. They are what? They are used as tranquilizers. So what we should know about barbiturates are they are sleep producing agents. That's why they are used as tranquilizers. Some other substances used are what Valium and serotonin. These are also barbiturates. Now, analgesics. Analgesics reduce or abolish pain without causing impairment of consciousness, mental confusion, and coordination. So, what analgesics are given what for treating pain, for lowering the pain of the patient. So, it can be classified into what non-narcotic or narcotic drugs. Non-narcotic drugs. Just remember that non-narcotic drugs are given for relatively milder pain, such as pain due to arthritis or something. Non-narcotic drugs are given for severe pain, such as due to what like cancer pain, such as very high level of pain. For that only we give narcotic drugs. The non-narcotic drugs, we have the examples what aspirin and paracetamol. So here we have the preparation method for aspirin here. We already learned this in other chapter what salicylic acid. We do acetylation. So we get what acetyl salicylic acid, which is the structure of aspirin. So what are narcotic analgesics? So narcotic analgesics are morphine and its commodotes. When administered in medicinal doses, these relieve pain. So what do these drugs do? They relieve pain and also they produce sleep. In poisonous doses, these produces stupor, coma, convulsions, and ultimately death. Morphine narcotics are sometimes referred to as opiates. Why? Because these are all obtained from opium poppy. See, these are used in severe pain, such as what? Post-operative pain, cardiac pain, pains of terminal cancer, and in childbirth. So for mild pain, non-narcotic, and for severe pain, we use narcotic drugs. So some structures are given here: morphine, heroin, and codeine. These are all what opiates. Now, antimicrobials. We need to learn about antibiotics, antiseptics, disinfectants. So what are antibiotics? Antibiotics are used as drugs to treat infections because of their low toxicity for humans and animals. So they are toxic for both humans and the pathogen. Pathogen means the disease causing organism, but this more harmful for the pathogen. That's why we are using it. So Paul Ehrlich first discovered what arsenic based compound called arsphenamine. Another name for this compound is salvarsan. What it is discovered for treating syphilis, and he got Nobel Prize for this discovery. And he observed that for both salvarsan and azodis, they have similar linkage of arsenic and nitrogen double bond. So while observing both these compounds, he came to the discovery of another antibacterial agent called protonsil. And he also discovered what protonsil is metabolized into sulfanilamide in our body, which is the active compound responsible for the antibacterial property of the drug. So we discovered this sulfanilamide is the active compound, and through that, many other sulfur drugs were discovered. So structures of salvarsan and protonsil. You can see that arsenic double linkage, and in protonsil there is this nitrogen double bond. And after that came what? Penicillin came, discovered by Alexander Fleming. It was revolutionary at that period. It was obtained from Penicillium fungus. Antibiotics have either chiral effect or static effect. So it can be chiral or static. Means chiral means it will kill the microbes. Static means it inhibits the growth of the microbes. A few examples of these two antibiotics are given here. So bactericidal, example is penicillin, aminoglycoside, or fluoxetine. Bacteriostatic, erythromycin, tetracycline, chloramphenicol. So antibiotics which kill a whole wide range of bacteria, gram positive and gram negative. If the antibiotic kills both of these bacteria, it is called what? Broad spectrum antibiotics. So examples for that are ampicillin, amoxicillin, chloramphenicol, vancomycin, and ofloxacin. Those effective mainly against either gram positive or gram negative. So the antibiotic only kills one group, either gram positive or gram negative bacteria. It is what? Narrow spectrum bacteria. Example for that is penicillin G. If effective against a single organism, or the antibiotic given is effective against a single organism or disease, it is called what? It is called limited spectrum antibiotic. Okay, now another example given in our text is dicydrazine. What it is? Toxic towards certain strains of cancer cells. So the structure of penicillin and chloramphenicol is given here. Now we'll learn about antiseptics and disinfectants. So what is the difference between them? Just think that antiseptics are used on living body and disinfectants are used on inanimate objects. Antiseptics are applied to the living tissues such as wounds, cuts, ulcers, and disease surfaces. So examples for antiseptic are furazine, soframycin, Dettol. And Dettol is a mixture of what? It's a mixture of chloroxylene and terpene, which is given in NCERT. Structures of both are also given there. Bitheanal. The compound is also called bithionol or bithional is added to soaps to impart what? Antiseptic property. Iodine is a powerful antiseptic. It's 2 to 3% solution in alcohol water is mixture known as what? Tincture of iodine. So 2 to 3% solution of alcohol iodine in alcohol water mixture is known as what? Tincture of iodine. Iodoform is also an antiseptic. Boric acid in dilute aqueous solution. What is an antiseptic for what? It's an antiseptic for ice. Disinfectants are applied to inanimate objects. I already told you disinfectants are used for inanimate objects such as what? Floors, drainage system, installations. Same substances can act as antiseptic as well as disinfectant. How? By varying the concentration of the reagent present. So for that example given in NCERT is 0.2% solution of phenol. This is what is an antiseptic, while 1% solution is a disinfectant. Chlorine in the concentration of 0.2 to 0.4 ppm in aqueous solution, and SO2 in very low concentrations are what? They are disinfectants. So example of disinfectants are given here what? Chlorine in concentration 0.2 to 0.4 and SO2. Now anti-fertility drugs. So they are used as essentially contraceptives. So it can be a mixture of estrogen and progesterone, or it can only contain progesterone. So norethindrone is an example of synthetic progesterone used as a contraceptive. An estrogen derivative is used for estrogen progesterone combination. What we use is ethinyl estradiol or novestrol. The structure of both are given here. So ethinyl estradiol is a combination of estrogen progesterone, and norethindrone is only a progesterone only formulation. Now chemicals in food. We have to learn about what? Artificial sweetening agents and preservatives. So we have given a chart and text some artificial sweeteners. Why we use artificial sweeteners? Because natural sugar, sucrose is what? It adds to the caloric intake of our body. So it's not good for our body. So instead we use artificial sweeteners. Examples are aspartame, which is 100 times sweeter than cane sugar. Saccharin 550 times. Sucralose 600. Altein 2000. Use of aspartame is limited to cold foods and soft drinks because it's unstable at cooking temperature. So aspartame is not stable at cooking temperature. However, sucralose is stable at cooking temperature. Altein is a high potency sweetener. See, altein is almost 2000 times sweeter than sugar. But we don't use it more often because what the control of sweetness is hard. Now, food preservatives, we have what examples are table salt, sugar, vegetable oils, and sodium benzoate. Now, some cleansing agents, soaps. Soaps are prepared by the process saponification. What is saponification? Soaps containing sodium salts are formed by heating fat. What is fat? Fat is a glycerol ester of fatty acid. So, glycerol we are combining with fatty acid. So, we will get a glycerol ester of fatty acid known as fat. So, we are combining that with aqueous sodium hydroxide or aqueous potassium hydroxide solution. So, we will get what? A soap. Here, we are forming sodium stearate, which is a soap. So, this process is known as saponification. So, some types of soaps we have learned about are toilet stage. Toilet soaps or what? We use excess alkali from toilet soaps and we add color and perfumes to toilet soaps. Soaps that float in water. How we beat air into the soap before hardening. So we will get soap that float in water. Transparent soaps are made by dissolving soap in ethanol. So we will dissolve soap in ethanol and then we evaporate the excess solvent. So we'll get transparent soaps. In medicated soaps, we add substances of medicinal value. In shaving soaps, we add glycerol or to prevent drab drying and another gum called water rosin. Why? Because sodium rosinate lather sweat. Laundry soaps contain fillers like sodium rosinate, sodium silicate, etc. Borax and sodium carbonate. Soap powders are scoring soaps contain some soap as scoring agent. Means an abrasive such as powdered pumice or finely divided sand. Okay, now we will have to discuss about hard water. And if the water contains some ions like calcium and magnesium, what the soap does not give lather well. So we have to due to why because it forms scum with these ions. So the reaction is given. Our soap reacts with these ions to form what? Insoluble calcium stearate. Here we are taking stearic acid. That's why we got calcium stearate, which is scum. So it cannot be used in many industries such as laundry industry, dyeing industry. So we had to create a detergent which gives foam even on or lathers on even in hard water. So such detergents are called synthetic detergents. So synthetic detergents can be classified into anionic, cationic, and non-ionic. Anionic detergents are examples given. So here the anionic part is the molecules involved in cleansing action. So we have many examples here. Sodium lauryl sulfate, sodium dodecyl benzene sulfonate, and all. So they are used for what? Household work, toothpaste. Cationic detergents, what here? The cationic part only is responsible for the action. So example for that is also given here. What? Cetyl trimethyl ammonium bromide. So it is used in air conditions, but it is not used very commonly because it is very expensive. Now, non-ionic detergents are what? They do not contain any ion. So example of that is this one. What? How it is formed? It's formed by stearic acid combines with polyethylene glycol. So it is used in what? It is used in liquid dishwashing detergents. So what the problem with detergents is that if the detergent is highly branched, it cannot be degraded easily by the bacteria. So when these are released into natural water bodies, they get accumulated in these and cause what? Cause forming in rivers, ponds, and streams. So they are generally. So we have government has placed measures to decrease the branching of the detergents so that they can be easily degraded by the bacteria. So that is all we have to say for this chapter. Thank you all.